Good morning, students. In previous lecture, we have discussed subgraphs and operations of graph and fusion of graph. Today, we will discuss walk, that means another types of graph, walk, trail, path, Eulerian graph, Hamiltonian graph. So we start with the walk. The screen is visible to you? Okay. So we start with the walk. These are other types of graph. So for definition of walk, we define as a finite alternative sequence. A finite alternative sequence of, that means vertices and edges. Vertices and edges. We define as V0, E1, V1, E2, V2, E3, and so on. And we write as Vk minus 1, Vk minus 1 as Ek, and Vk, Ek plus 1, and so on. Number of phases. The beginning and ending, we write as Vk plus 1. The beginning and ending with the vertices. With the vertices such that that means we define as J lie between 1 to k when we using k in vertices or edges. So and Vj are the beginning vertices, sorry, beginning and ending vertices, Vj, beginning and ending vertices of the as Ej. Here all the edges are distinct. So the graph, then we write it, then the graph is called a walk of the graph G. Called a walk of the graph G. Here in a walk, vertices can be repeated. Because we start with the initial vertex. We start with initial vertex V0, and we also end with the vertex Vk plus 1. Suppose. So when we start our walking, that means you can start walking from source x1 and visit by the as is. That means you can take an example of park. So many roads are there in the park. When you start at the initial point and move all the road in the park and back to the same point. So this is known as the walk. But you cannot visit the edges twice or thrice. You can visit all the vertices. Vertex may be repeated because the initial and ending vertex are same. So we can take an example here. For example, that means we have some so we define as this is the vertex v1, this is the vertex v2, this is the vertex v3 here v3 and v4 and v5, this is vertex v5 and vertex v6. So for v1 to v2 the as is e1 here, this is as e2, as e3, as e4, this we write as e5 and this we can fix as E6, E7, E8 and E9. So total number of edges we use is 9. 9 edges and 6 vertices. So when you start visiting, so that means when you start visiting from vertex V1, move to the as E1, that means you choose this as E1, then visit to V2, then E2, then V3, E3 and V4, E5, V4, E5 and you can visit vertex V2 again and E6, then vertex V5, then E8, then V6, then E9, then V1. Then V1. So this is the walk. Vertex may be repeated. So we in a walk we can have visit vertex more than once. So there is no issue. We some edges are left, then you can visit more than once. So in note we can write as in walk vertex can appear more than once. Vertex can appear more than once. So we choose the graph. That means this is our walk. So this walk and this is the graph G. Walk is always a subgraph of graph G. Walk is always a subgraph of graph G. And self loop is also be the part of the graph G. Self loop maybe you can write as maybe be the part of graph G. So you can write here as V5 to E7 here. You can write as V5 to E7, then V5, then E8. You can add. So then E8. So the self loop is also the part of the walk. Self loop be also the part of the walk. So an finite alternative sequence, that means we have finite number of vertices and edges. Alternative sequence, that means we start visiting from vertex and end also with the vertex, and make a walk. Initial and starting vertex are same. Is said to be a walk. Yes, Ankita? Okay. Noted? Okay. Now we define open walk. The part of the walk next is open walk. As the name of open walk means the initial and the ending vertex are distinct, is known as the open walk. Open walk, we start with vertex V1 and end up to the another vertex V3, V4. So such type of graph is known as open walk. So a walk is called open. A walk is called an open walk if its initial or ending vertices are different. Initial and ending, or we write as terminal. Initial or ending vertex are distinct. Initial and ending vertex are distinct. So such type of graph is known as the open walk. So any graph is given, so we make a open walk, that means the initial and ending vertex are distinct. So the graph is known as open walk. So we can take an example of graph G. For example, this is a graph. We have the graph G. We write as so this is the vertex V1, this is the vertex V2, and having as E1, this is vertex V3, we write E3, E2, and we write V4, this is E3, and E5, V5, E6, V6, V7, E7, or you give the E8 and E9, E8 and E9. We have 7 vertices and 9 edges. 9 or 2 are remaining. E10. This is E10 and E11. So 7 vertices and 11 edges in this graph. This is the graph G. This is the graph G. So we make the open walk of this graph. So you can construct any of the graph, that means the initial and terminal vertex are distinct, is known as the open walk. Open walk, that means you just draw this, move to this, and visit to this side, and also visit to this side, and also visit to this side and this side. So this is the example of open walk. We use this path. You understand? We use this path, that means this side, this, and this side, and this side, and this path, and this. So this is the example of open walk. So initial and terminal. So this is the initial vertex when we use as initial, and this is terminal vertex. So initial and ending. So initial, this is V1, and here terminal vertex, last vertex is V7. So initial and terminal vertex are distinct. When we join, that means V7 to V1. So this is the example of closed walk. So next definition, we choose the closed walk. Okay. So when initial and terminal vertex are distinct, so such type of graph is known as the open walk. You are noted? Noted? Payal, Anshuma. Okay. You mention all the as is we use here. This is as E1. Okay. E1, E2, and here this is V3. This is vertex V2, and here E3, and this is E5. This is V4, V5, E6, V6, and E7. So you can, because we make the alternative sequence, so we write in the sequence form. Now we define closed walk. Okay. Next we define closed walk. So this is the example of open walk. That means initial and terminal vertex are distinct, but in closed walk, so we write the definition: a walk is said to be closed if its start and ending vertex are same. Ending vertex are same. Start and ending vertex are same. So when we start our visiting, then end that visiting. So in define that we visit vertex V1, V3, V5, then add to the vertex V1. So such type of graph is known as the closed walk. So initial, that means, and ending vertex are same. So we can take an example. So the example of closed walk. This is the graph G. V1, V2. V1, V2, V3, V4, V5, and V6. This is the graph G. So the closed walk. So for closed walk, we take simple this example. That means we visited all the vertices and back to the. So here V1, that means V1, you can give the name as E1, E2, E3, E4, E5, and here E6, E7, and E8. So this is V1, E1, V2, E2, V3, and we visit V8, and here V6, E7, and V5, and this is V4 and E5. So finite alternative sequence. We make a alternative sequence. Sequence is that means V1 E1, V2 E2, V3 E8, V6 E7, and V5 E4. This is V5, E7, E8. Here you give the name E9, V5, E9, V4, E5, and V1. So here initial and ending. That means the initial and terminal vertex of the graph are same. So such a type of graph is known as the walk. So we make a alternative sequence. Vertex may be repeated. That means when we start from V1 and end to the vertex V1, so initial and ending vertex are same, so then vertex may be repeated. So such type of walk is known as the closed walk. That means make a circuit form. Noted? Okay. Now next is trail. We define trail. So the trail is also a finite alternative sequence. We define as a finite alternative sequence. A finite alternative sequence from vertex V0 to vertex Vk in a graph G. In a graph G is called a trail. Is called a trail if it does not. This is important point. If it does not contain a repeated edge. Does not contain a repeated edge. So this is important here. So in trail, you cannot repeat the edges. That means when you visit once, so then you cannot repeat the same as twice, thrice. So when you start visiting from this, that means V0 E1, V1 E2, V2 E3, and visit all the vertices Vk minus 1 and Ek, and last is Vk. So such type of graph is said to be a trail. Contain no repeated edge. We can write as all edges are distinct. You have to remember all edges are distinct, where j lie between 1 to k. When we use k vertices, so that means ek, k is used. So all the edges are distinct. So this is known as the trail. Finite alternative sequence, we make same definition in walk, but here the edge doesn't repeat it. In walk, the repetition of edges or vertices are allowed, but in trail, no edge will be repeated. Okay. So this is the second definition. First is walk. Walk also make a finite alternative sequence of vertices and edges. Two types of walk, open and closed walk. And this is trail. Trail also a finite alternative sequence, but is doesn't repeated. As is does not repeated. And we cannot visit twice, thrice of any particular edges. Next, we define path. Approximately similar definitions, but little bit difference is some graphs having repeated vertex, some are repeated edges, some not repeated vertex, not repeated edges, but make a finite alternative sequence. But depend upon the vertices, repetition of vertex are allowed or not, repetition of edges are allowed or not. So we make a comparison table when we define all the graphs such as walk, trail, path and circuit. Then we make a compare table. So which graph allow repetition of vertices, which graph allow repetition of edges. So we can understand or remember all the definitions. Okay, you noted it? Definition of trail. In trail does not contain a repeated edge. Now we define path. Path, a open walk. A open walk. We use open walk. Open walk, we define open walk as the initial and terminal vertex, ending vertex are distinct. So in a path, we define a path that is a open walk from vertex V0 to vertex Vk is called a path or simple path. Path or simple path if it does not contain a repeated vertex. Contain a repeated vertex. Contain a repeated vertex. So here you understand this, in path it does not contain a repeated vertex, and thus necessarily all the edges. That means visit all the edges. So the simple path we write as V0 E1, V1 E2, V2 E3 and Vk minus 1, Ek and Vk. So where all the edges, that means we define as Ej and vertex Vi are distinct. This is the restriction in path. So J defined as 1 to K and I defined from 0 to K. That means we use a vertex from V0 to Vk. So vertex Vi we denoted as I and J. That means edges we starting from E1 to Ek. So this represents the So you understand the definition of path. Path means a open walk. open walk. This is obvious, that means the initial and ending vertex are distinct. Is said to be a path or simple path if it does not contain a repeated vertex. That means we cannot visit any vertex twice or thrice, and thus necessarily all the edges. Also, all the edges we cannot repeat. So the simple path we make as 0, 1, and so on. So you can understand this. In path, no vertex and edges are repeated. No vertex and edges are repeated. Okay. So we define closed walk, trail. So finite alternative sequence from V0 to Vk is a, in a graph C is called trail if it does not contain a repeated edge. It does not contain a repeated edge. That means vertex may be repeated, but A is not repeated. But here it does not contain a repeated vertex and the necessary all the edges and digit all the edges. So how to relate these two graphs? That means in the note we can write as every simple path, yeah, simple, we write as path, every simple path is also a trail. Yeah, every trail is a simple path. This is correct, or we can write as every trail is a simple path. Every trail is a simple path. This is correct. According to definition, the first one is correct. Second is not correct. So every simple path is a trail. But in simple path, this is the restriction. No repeated vertex and edges are allowed. But in trail, no repeated edges are allowed. Vertex may be repeated. So then, but in path, no vertex will be repeated. That means a simple path is a trail. A simple path is a trail. You can understand. Second, a self loop. A self loop be the part of walk, but not a part of path. Not a part of path. Understand? Because when a self loop is given, so that means this is necessarily to be visit a vertex twice. When we visiting all the edges, so then a particular vertex which have self loop, we visit that vertex twice. So in path, no self loop is allowed. So you have self loop, so then the graph is not a path. Number 3, in a path, the terminal vertices are of degree 1 and rest of vertices are of degree 2. Rest of vertices are of degree 2. So these are three important points. So we have to remember, that means we relate to trail, that means path, trail and walk. And you noted Akansha, Namika, Payal. Myself. Okay. Okay. Now next, circuit. Circuit. So a circuit is a closed walk. Is a closed walk. That means initial and terminal vertex are same. A circuit is a closed walk that contain all vertices so we write as it is also known as a simple cycle, known as a simple cycle if the part of a graph contain a cycle. So that means closed block that contain all the vertices. It is also known as simple cycle if, that means this is another definition, if the part of the graph contain a cycle. So that means if you have an example, such type of example, that means this is the example of graph G. That means we defined as vertex V1, V2, V3, V4 and V5. We have five vertices and edges, corresponding edges, and the subgraph, that means the circuit. The circuit is this is for contain all the vertices. Contain all the vertices. That means this is structure. This is structure. That means contain all the vertices. This is vertex V1, vertex V2, V3, V4, and V5. This shows the circuit of the graph. That means initial and ending, because this is defined as a closed walk. Closed walk means initial and ending vertex are same, and we write as that contain all the vertices. It is also not a simple cycle, also known as simple cycle, if it contain a part of the cycle. That means if we take an example, that means we consider this portion. We consider this portion V1, V2 and V3. So this is known as the simple cycle. Simple cycle. But this doesn't cover all the vertices. But this construct a circuit. This construct a circuit. That means the initial and ending vertex are same. So construct a circle, so known as the simple cycle. This is the simple cycle, and this is the circuit or cycle graph. Circuit or cycle graph, both are same. So we study walk, open walk, closed walk, trail, path, and circuit. So in circuit we make a sequence because we give the name of the edges, that means E1, E2, E3, E4, E5 and E6. So we make a sequence, that means V1, V1, E1, V2, E2, V3, E3, V4, E4, E4 and V5 E5 and V1. So here we see that the initial and terminal ending vertex are same. So be the example of closed walk or also example of the circuit. So a closed walk is said to be a circuit. So just you remember, that means which make a circuit form, any graph. Just we write as a part of the graph having contain a cycle. So also the example of cycle graph or circuit. So that means we can say that a self loop be the part of cycle, be the part of circuit or cycle. Circuit we write as part of circuit because we having only just one vertex. So this vertex 1, that we having as E1. So we write a sequence that's E1, V1, E1, V1, E1, V1. So this is the alternative sequence. So a self loop be also the part of the circuit. A self loop. But in other form, that means we write the second. So that means a circuit is non-intersecting. Non-intersecting walk. That means the edges not intersect to each other. Non-intersecting walk such that every vertex is of degree 2. Is of degree 2. So degree more than 2, so that this may be possibility. So the edges will be intersect to each other. Here you can see that if the degree, that means we see that the degree of this vertex is 2, the degree of this vertex is 3, degree of this vertex is 3. Otherwise, all vertex having degree 2, 2. So we see that means here you choose this type of graph, that means which having every vertex having degree 2, this vertex having degree 2, this vertex having degree 2, this vertex having degree 2. So this is the example of circuit. So every vertex having degree 2. Every vertex, when any vertex having degree more than 2, so that means this will be intersect. So we cannot visit sometimes the particular edge. So we make a table on the basis of all the graphs. So we write here the graph, and first we write as repeated as, second we write repeated vertex, repeated as, repeated vertex, or last start and end vertex. Okay, so we will do next lecture. Thank you, students. Thank you.